This is Softwareable Bytes. Hello and welcome to another episode of Softwareable Bytes. This is the show where I read to you articles and blog posts on subjects like software and cloud engineering and architecture, site reliability engineering, DevOps, and everything in between. Today's episode is a continuation of the previous episode. So if you are new here, it's better that you listen to that episode first. But if you are all caught up, let's continue with part 2. The service mesh. What every software engineer needs to know about the world's most overhyped technology. By William Morgan of Buoyant.io. Part 2. Who does the service mesh help? As inconvenient as it may be, it turns out that in order for technology to actually have an impact, it must be adopted by human beings. So who adopts the service mesh? Who benefits from it? If you are building what I've described above as modern server software, you can roughly think of your team as divided into service owners who are in the business of building the business logic, and platform owners who are building the internal platform on which these services run. In small organizations, these may be the same people, but as the organization gets larger, these roles typically get more defined and even more subdivided. There's a lot more to be said here about the changing nature of DevOps, the organizational impact of microservices, etc. But for now, let's take these descriptions as a given. Seen through this lens, the immediate beneficiary of the service mesh is the platform owners. The goal of the platform team, after all, is to build the internal platform of which the service owners can run their business logic, and to do so in a way that keeps the service owners as independent as possible from the gory details of operationalization. The service mesh not only provides features that are critical for accomplishing this, it does so in a way that doesn't, in turn, incur a dependency on service owners. The service owners also benefit, albeit in a more indirect way. The goal of the service owner is to be as productive as possible in building the logic of the business and the fewer operational mechanics they have to worry about. Rather than being on the hook for implementing, for example, retry policies or TLS, they can focus purely on business logic concerns and trust that the platform will take care of the rest. That's a big plus for them as well. The organizational value of the decoupling between platform and service owners can't be overstated. In fact, I think it might be the key reason why the service mesh is valuable. We learned this lesson when one of our earliest Linkerd adopters told us just why they are adopting a service mesh, because it allowed them to not have to talk to people. This was a platform team at a large company that was migrating to Kubernetes. Because this app handled sensitive information, they wanted to encrypt all communication on the clusters. There were hundreds of services and hundreds of developers teams, and they were not looking forward to convincing each dev team to add TLS to their roadmap. By installing Linkerd, they shifted ownership of the feature out of the hands of developers, for whom it was an imposition, and into the hands of the platform team, for whom it was a top-level priority. Linkerd didn't solve a technical problem for them so much as it solved an organizational problem. In short, the service mesh is less a solution to a technical problem than it is a solution to a socio-technical problem. Does the service mesh solve all my problems? Yes. No. If you look at the 3 classes of features outlined above, reliability, security, and observability, it should be clear that the service mesh is not a complete solution for any of these domains. While Linkerd can retry requests when it knows that they are idempotent, it can't make decisions about what to return to the user if a service is entirely down. The application must make these decisions. While Linkerd can report success rates, it can't look inside a service and report internal metrics. The application must have instrumentation. And while Linkerd can do things like mutual TLS for free, there's a lot more to security solution than just that. The subset of features in those domains that the service mesh provides are the ones that are platform features. By this, I mean features that are 1. Independent of business logic. The way that traffic latency histograms are computed for calls between foo and bar is totally independent of why foo is calling the bar in the first place. 2. Difficult to implement correctly. Linkerd's retries are parameterized with sophisticated things like retry budgets because the naive approach to retry is a sure path to retry storms and other distributed system failure modes. 3. Most effective when implemented uniformly. The mechanics of mutual TLS only really make sense when everyone is doing them. Because these features are implemented at the proxy layer rather than at the application layer, the service mesh provides them at the platform level, not application level. It doesn't matter what language the services are written in, or what framework they use, or who wrote them, or how they get there. The proxies function independent of all that, and the ownership of this functionality, including the operational ownership of configuration, updates, operation, maintenance, etc., lies purely at the platform level. Example features of the service mesh. Service mesh, observability, service success rates, reliability, request retries, security, mutual TLS between all services. For platform, non-service mesh. For observability, log aggregation. Reliability, multiple replicas of dataset. And security, encryption of data at rest. Application. For observability, instrumentation of internal feature usage. Reliability, handling of failure when an entry component is down. For security, ensuring users only have access to their own data. To summarize, the service mesh is not the complete solution to reliability, or to observability, or to security. The broader ownership of these domains necessarily involve service owners, ops, and SRE teams, and other parts of the organization. The service mesh can only provide a platform layer slice of each domain. Why does the service mesh make sense now? At this point, you may be saying to yourself, okay, if this service mesh thing is so great, why weren't we rolling millions of proxies in our stack 10 years ago? There's a shallow answer to this, which is that 10 years ago, everyone was building monoliths, and no one needed a service mesh. Which is true, but I think misses the point. Even 10 years ago, the concept of microservices as a feasible way to building high-scale systems was widely discussed, and was publicly being put into practice at companies like Twitter, Facebook, Google, and Netflix. The general sentiment, at least in the parts of the industry I was exposed to, was that microservices were the right way to build high-scale systems, even if, gosh, they were really painful to do. Of course, while there were companies operating microservices 10 years ago, they were by and large not installing proxies everywhere to form a service mesh. If you look closely though, they were doing something related. Many of these organizations mandated the use of a specific internal library for network communication, sometimes called a fat client library. Netflix had Hystrix, Google had the Stubby libraries, and Twitter had Finagle. Finagle, for example, was mandatory for every new service at Twitter, handled both client and server sides of the connection, and implemented retries and request routing and load balancing and instrumentation. It provided a consistent layer of reliability and observability across the entire Twitter stack, independent of what the service itself actually did. Sure, it worked only for JVM languages, and it had a programming model that you had to build your whole app around, but the operational features it provided were almost exactly those of the service mesh. So 10 years ago, not only we did have microservices, we had proto-service mesh libraries that solved many of the same problems that the service mesh solves today. But we didn't have the service mesh. Something else needed to change first. And that's where the deeper answer lies, buried in another difference that's happened over the past 10 years. There's been a dramatic reduction of the cost of deploying microservices. The companies I've listed above, who were publicly using microservices a decade ago, Twitter, Netflix, Facebook, Google, were companies of immense scale and immense resources. They had not just the need, but the talent to build, deploy, and operate significant microservice applications. The sheer amount of engineering time and energy that went into Twitter's migration from monolith to microservices boggles the imagination, and this sort of infrastructural maneuver was essentially impossible for smaller companies. Contrast that to today, where you might encounter startups with a 5-to-1 or even 10-to-1 ratio of microservices to developers, and what's more, they were equipped to handle it. If running 50 microservices is a plausible approach for a 5-person startup, then clearly something has reduced the cost of adopting microservices. The dramatic reduction in the cost of operating microservices is a result of one thing: the rise in the adoption of containers and container orchestrators. And this is where the deeper answer to the question of what change has enabled the service mesh lies. What's made the service mesh operationally viable is the same thing that's making microservices operationally viable: Kubernetes and Docker. Why? Well, Docker solves one big thing: the packaging problem. By allowing you to package your app and its non-network runtime dependencies into a container, your app is now a fungible unit that can be thrown around and run anywhere. By the same token, Docker makes it exponentially easier to run a polyglot stack, because the container is an atomic unit of execution. It doesn't really matter what's inside the container, and whether it's a JVM app or a Node app or Go or Python or Ruby, you just run it. Kubernetes solves the next step. Now that I have a bunch of executable things, and I also have a bunch of things that can execute these executable things, aka machines, I need a mapping between them. In a broad sense, you give Kubernetes a bunch of containers and a bunch of machines, and it figures out this mapping, which of course is a dynamic and ever-shifting thing. As new containers roll through the system, machines come in and out of operation, and so on. But Kubernetes figures it out. Once you have Kubernetes going, the deployment time cost of running one service is not that much different from running 10 services. And in fact, not that different from 100 services. Combine that with the container as packaging mechanism that encourages polyglot implementations, and the result is a ton of new applications that are implemented as microservices written in a variety of languages. Exactly the environment the service mesh is most suited for. And so finally we come to why the service mesh is feasible now. The very same uniformity that Kubernetes provides for services is directly applicable to the operational challenges of the service mesh. You package the proxies into containers, you tell Kubernetes to stick them everywhere, and voila, you got yourself a service mesh, with all the deploy time mechanics handled for you by Kubernetes. To summarize, the reason why the service mesh makes sense now, as opposed to 10 years ago, is that the rise of Kubernetes and Docker have not only dramatically increased the need to run a service mesh by making it easy to build your application as polyglot microservices architecture, they've dramatically reduced the cost of running a service mesh by providing mechanisms for deploying and maintaining fleets of sidecar proxies. You just listened to part 2 of The Service Mesh, what every software engineer needs to know about the world's most overhyped technology, by William Morgan of Buoyant.io. Listen to part 3 on the next episode. And if you're looking for software and cloud development services and training, check out softwareable.com. We help customers in their software and cloud journey, whether it is taking software from ideas to complete solutions, migrating existing systems to the cloud, or mentoring and training individuals and teams. We make it work for your needs. Go to softwareable.com, that's software without the E, IBLE.com, to learn more. Okay, let's now check the tool of the day. Today's tool is Windows 95. Wait, what? Well, it's Windows 95 running in an Electron app. Sorry, this is for the lols and nostalgia. But does it work? Yes, quite well actually, on macOS, Windows, and Linux. Bear in mind that this is written entirely in JavaScript, so please adjust your expectations. Now the million-dollar question is, does it run Doom? You'll likely be better off with an actual virtualization app. But the short answer is yes. Thanks to @displacedgamers, I can recommend that you switch to a resolution of 640 by 480 at 256 colors before starting DOS games, just like the good old days. Find the link to this in the description of this episode. And that should do it for another episode of Softwareable Bytes. Have a great rest of your day, and I'll see you here again in the next episode.